and gentlemen. Today we're talking about section 2.5, which is reasoning using properties from algebra. So we're going to combine algebra topics that we've covered before, and then add in some of the logical reasoning involved that we've talked about a little bit with deductive reasoning, and that will eventually be applying to geometry. So, first of all, let's start by solving the equation for x, and we're going to end up giving reasons or justification backing up what we did for why we did it. So here, to get x by itself, I'll start by subtracting 8x from both sides. If you do this in a slightly different order, you'll still get the correct answer. On the left side, 4x minus 8x is negative 4x. I bring down my minus 12, my equal sign, and these cancel. That equals negative 4. Secondly, now that my x's are all on the left, I want to get all my numbers over to the right. So I'm going to add 12 to both sides. So they cancel on the left, and I'm left with negative 4x equals positive 8. And to get rid of my negative 4 coefficient, I'll divide both sides by negative 4. So these cancel. I'm left with x is negative 2. Now, as far as reasons go, we're going to look at different properties we can use to state as reasons for all of our steps. Those properties are as follows, and we'll come back to that problem. They're all called properties of equality because these properties say what you can do and make an equation still remain equal. So for example, the addition property. Let's say we have a statement that states that A equals B. Well, what I can do is I can add the same number to both sides of my equation and it still remains equal. So A plus 4 equals, equals B plus 4. Where I just added the plus 4 to both sides. So just like when we're solving an equation, if we add something to one side, we have to add it to the other side, and if we do that, it remains equal. So that's our addition property of equality. Same thing for subtraction. If I start again with A equals B, I can subtract the same number from both sides, so let's say minus 4 on both sides, and my equation still remains equal. I can keep my equal sign there. So again, we just subtracted the same thing from both sides. Multiplication and division work the exact same way. For multiplication, if I start with A equals B, I can multiply both sides by the same number. So 4 times A equals 4 times B, multiplying both sides by the same number. And division property, I can start with A equals B and I can divide both sides by 4 or any number, and it still remains equal, as long as I don't divide by 0, because that is not possible, so we can't divide by 0. But those are the 4 basic properties that we use when we're solving equations. You add, subtract, and multiply, and divide things on both sides. The last one is the substitution property, which you've already seen in Algebra 1 as well. That states if I have an expression like 2a plus 4, and I know that a is 2, I can simply plug in 2 for a. So this would be 2 times 2 plus 4. So substitution is just when you plug something in. So when you plug in a number, technically we call that substituting or substitution. So going back to our original equation, when we subtracted 8x from both sides, we started by using our subtraction property of equality, or I'll abbreviate and say subtraction property. And then when stuff cancels, we usually just call that simplifying. Anytime things cancel. Or just cleaning up and simplifying our equation. So those cancel, and we rewrite it as negative 4x minus 12 when we combine these like terms. These cancel, and then we're left with our negative 4. So that's simplifying. Next, we added 12 to both sides. So that was our addition property of equality, or I'll just say addition property. And when our 12s canceled, we were left with negative 4x, and our negative 4 plus 12 gave us 8. That was simplifying. Next, we divided both sides by negative 4, so we used our division property. And when these canceled, we were left with x, and 8 divided by negative 4 was negative 2, so that was again simplifying. Now, all the time, if you don't show the simplifying step, or for example, if you see a problem in your textbook and they don't show the actual step simplify, then for that particular textbook problem, you do not have to write it. But as a rule, if you're doing something from scratch, I should see every step, including the simplifying steps. All right? Let's try another one. For this one, if we start with negative 4 times the quantity 11x plus 2 equals 80, we start by using our distributive property. We distribute negative 4 into both pieces. So negative 4 times 11 is negative 44x, and negative 4 times 2 is negative 8. So we start with our distributive property, another property that we used in Algebra 1. Next, to get x by itself, we'll add 8 to both sides. So that's our addition property. And then we cancel stuff and simplify. So these cancel, so we have negative 44x. And if we add these together, we have 88. So that was our simplifying step. Next, we need to get rid of this negative 44. So we divide both sides by negative 44. Our division property of equality. And last, we're going to simplify. These cancel, so we're left with x, and 88 divided by negative 44 is negative 2. So our last step is simplify. So those are all of our reasons for each step that we took. Again, any questions, feel free to see me before or after school, or rewind the video and check out some other examples, or ask a friend in class. So those are our properties from algebra. Well, let's look at properties that we're going to use more often in geometry. 3 of them in particular, and again, these are always posted in the classroom. The reflexive property of equality just always states that something is equal to itself. So for example, if we're dealing with real numbers, so let's say a is a real number, we're saying that a is equal to itself. We're talking about segment lengths. We can say that segment length AB equal to itself. Angle measures, the measure of angle A is always equal to itself. And again, we'll go through examples in section 6 about when we really need to use the reflexive property, because right now it seems so common sense that why do we even go over it? Of course something is equal to itself. But we'll talk a little bit more about that when we talk about geometric proofs, which we'll get to soon. Our symmetric property says that the order doesn't matter, referring to when you say things are equal. So if we say that A equals B, in other words, B equals A. The order of those two doesn't matter. If we talk about segment length, we can say the segment AB is equal to the length of segment CD, or the order doesn't matter. We can say the length of CD is equal to the length of AB. We can switch the order, doesn't matter. Angle measures, the measure of angle A equals the measure of angle B. Order doesn't matter, so I could say the measure of angle B equals the measure of angle A. Now you've seen that before in algebra. If I were to say, if I would solve an equation and say that 4 equals x, or if you ended up with x equals 4, both are saying the same thing. So both are okay. That's using your symmetric property. The order does not matter. You can rewrite it either way. Transitive property of equality is a joy, so let's look at the transitive property. Transitive property is just like something we've seen before. And let me do this different color. It's just like the law of syllogism. So for example, if I were to say if A equals B, let me write that, and B equals C, then I can say that A equals C. So I'm taking whatever is in the middle and cutting it out, and leaving what's first and what's last. So I'm saying that A equals C. Exact same thing we did with the law of syllogism. You cut out the common interior and leave what is left, A and C. So if A equals B, then B equals C, then A equals C. Another way I like to look at it is this. You see trans in the beginning of transitive property. Well, I think of trans fat, which a lot of foods are advertised to have 0 trans fat because trans fat's bad. So a lot of people like to cut trans fat out of their diet. So I think of this as cutting out the trans fat. So you're cutting out something here in the middle. You're cutting out this trans fat, this extra stuff that you don't really need. For looking at segment length, I can say that if the length of AB equals the length of CD, and the length of CD equals the length of XY, then I can cut out the common stuff, the CD, and just leave AB and XY. So AB equals XY. Because if AB is 7, then CD must be 7. If CD is 7, XY is 7. So AB is the same as XY. It's just a string of logic. Same thing with angles. If the measure of angle A equals the measure of angle B, and the measure of angle B equals the measure of angle C, then cutting out the middle, the measure of angle A is equal to, you guessed it, the measure of angle C. So that's our transitive property. They all work with numbers, segments, segment lengths, and angle measures. And we'll use them mainly with segment lengths and angle measures in geometry. So let's name the property of equality, that the statement illustrates. So for number 4, if the measure of angle 6 equals the measure of angle 7, then the measure of angle 7 equals the measure of angle 6. All we did was switch the order of our 6 and 7. So that's going to be the symmetric property, saying the order doesn't matter when you're saying two things are equal. For number 5, if JK equals KL, the lengths, and the length of KL is 12, then the length of JK is 12. So we just took the KLs and cut them out, and we can just say that JK is equal to 12. That is our transitive property, same as the law of syllogism or cutting out this trans fat. And our last one, the measure of angle W equals the measure of angle W, or equals itself. That is reflexive. So those are examples of where you might see those in real life. Not real life, I'm sorry, in geometry. Well, geometry is in real life, so I guess that's okay to say. And let's look at one final challenge problem using some more geometry. We talk a lot about these types of problems in 6 and 7, so don't worry if it's somewhat of a struggle at first. We will get the hang of it. Sometimes it takes a little time. And let me number these first because I like to number things because I'm a math person. And I like to keep things in order. So, in the diagram, the length of AB equals the length of CD. And so you see those congruent marks to note that. We want to show that AC, the length of AC, is equal to the length of BD. Well, let's go through their logic and give reasons for each of the steps. For the length of AC equaling the length of AB plus BC, let's go to the picture. So they're saying the length of this whole piece is the same as adding these small pieces together. So adding their two pieces equals the length of the whole thing. We talked about that in chapter 1. If we're adding segments together, that is postulate 2. That is our segment addition postulate. So we're adding our two pieces to equal the whole thing. For number 3, we're doing the same thing. We're saying that BD, the whole thing, is equal to adding BC, piece 1, and CD, piece 2. So that, again, is our segment addition postulate. We're adding segments together to equal the whole thing. So our first two steps were simple to give reasons for them. For step number 4, it looks like for step 4, they started with our beginning statement, which was given to us, because it was given in the problem and it was given up here, so our reason was just given. So we're starting with the fact that AB and CD are equal. And it looks like they just added BC to both sides. Well, if we add the same thing to both sides, then it's using our addition property of equality. So we are using properties of equality here. It's just that not all of them are properties of equality. We use the postulate as well. And we use given information. And our last step, and this is the step that can kind of trick people up, so let's take it slow. They went somehow from this statement to this statement. Well, how did they do that? There's no AC up here. There's no BD up there. Well, we know that AB plus BC is equal to AC. So since they're equal, we just substituted AC for this guy. So this guy turned into AC. Similarly, we went from CD and BC to BD. Well, CD plus BC equals BD. So instead of writing this whole thing, we just wrote BD instead. So for that, we just substituted. Use the substitution property of equality. If you want to look at it visually at the picture, if it's still not clicking quite, we know that we're talking about AB plus BC. AB plus BC. Well, together that makes AC. So really we're saying the same thing. If you're adding these two together, you can look at them as two different segments pushed together, or you can just look at it as the whole segment itself. So instead of writing the two pieces separately, we just wrote them together, AC. Same thing, instead of writing these two segments separately, CD and BC, we wrote it as the whole thing, BD, instead. So instead of keeping the two pieces separate, we wrote them together. We just substituted different language, so it's the substitution property of equality. We will talk a lot more about these types of problems in section 6 and 7, but this is kind of an introduction with how we can justify our steps or give reasons using properties and postulates from geometry. And that concludes section 2.5.